So if we are given two random variables, their complete description is using their joint density function, which is a non-negative function. And if you want a physical interpretation, if you ask what is the probability that x is between x1 and x2, and at the same time y is between y1 and y2. So that's given by the area under the density function where x goes from x1 to x2, y goes from y1 to y2. So that's the meaning of the density function. So if you consider the x-axis and the y-axis, if you take x extend x plus delta x, remember the function is here, a three-dimensional function. So what is the probability that the activity in the x-axis is here and y-axis is here is given by this three-dimensional volume with x integrated from x1 to x2, and y integrated from y1 to y2. So the whole area is, of course, a whole volume is 1, and consequently this will be a number less than 1 representing the probability. So that's another interpretation of the joint density function. If you are given the joint density function, you can also get the marginals by integrating out the other variables. So to get the density function of x, you integrate out y, etc. We have gone through that. So like the mean and variance, the next question is how do you find out certain parameters which gives you a joint description about x and y. So of course you can look at mu x, but this only gives you a description about x because this is the average value, which is x fxx dx. And if you want one more parameter, generally that's the variance, which is variance of x, which is actually the mean squared error because it's x minus mu x. So it's the deviation of the random variable around the mean. Deviation could be plus minus. So we square it and take the average value. So it's the average or mean square error if you call x minus mu to be an error. Or x is the actual occurrence. So how far, what is the, on average, how far is this actual occurrence from the mean? So if that is far, then this quantity is going to be large, and this is a measure of the deviation. If all the activities are around the mean, then this error will be small and variance will be small. In any case, variance is a non-negative number. So these are the descriptions about one random variable. We would like to find something about two random variables. So in general, if I define z to be g of x comma y, we want an expected value of z. Of course, if z is a random variable, this is z. If you know its density function, then we can compute this in this manner. But you can also express this using because recall, after all, we are only interested in x and y. So that's a function of x and y. We should be able to write this in terms of joint density function of x and y. So the way it goes is you look at the probability that z is between z and z plus delta z. So this is easy. This is FCC multiplied by delta z. But z is, when the random variable z equal to xy, so the correspondingly here you could say this is z corresponds to gxy, and z plus delta c is variations on x and delta c. So if you solve this equation z equal to gxy, there may be multiple solutions to it. So for example, x1 comma y1, x2 comma y2, etc. may be solutions to this. And so when you make a small variation on this, there will be, each of these points will move around and you get a small region around here. So in the z domain, as z goes between z and z plus delta z, in the x domain, of course, the corresponding probability density function is fxy will be over these regions. So you can see that clearly this probability is summation of f of xi comma yi summed up over all these delta xi, delta yi regions. Now if I multiply this side with the z, I multiplied this side with the z is gxy. And if I sum over this is a quick proof, you also sum over the xy regions. But this summation together with this integration, we could write this as gxy, fxy, dx dy. And on this side, you have integral z fz dz. But this is the expected value of z. So on the right side, this is the expected value of gxy. So important thing is I just need that last formula. So if you have a function gxy, we can find its expected value of gxy is double integral the function gxy multiplied by the density function dx dy with the appropriate limits. I'm just going to put it as so this is a useful formula. We could use this to answer the question about finding parameters which describe the two random variables together. So in particular, from here you have expected value of xy. If you take gxy to be xy, so here you have xy multiplied by fxy, x comma y, dx dy. So in here, there's an interesting special case. Suppose x and y are independent. Then we have fxy, x comma y is of course fxx multiplied by fyy. So in that case, notice that this becomes expected value of xy becomes integral, double integral xy, fxx, fyy, dx dy. But you notice that now the integral splits. You can write this as x fxx dx, integral y fyy dy. But each of them is expected value of x and y. So we have a result here. If x and y are independent, then expected value of xy is mu x multiplied by mu y. In fact, a little more general, you could see that if gxy happens to be, let's say, hx multiplied by s of y, two different functions, then expected value of gxy is actually double integral hx multiplied by fx, which will be expected value of hx, multiplied by integral sy multiplied by fy. So that will be this way. So this is a special case of this. So we can use this to, especially this formula, to define something analogous to the variance. But involving two random variables. Remember, variance of x is expected value of x minus mu x the whole squared. Similarly, variance of y is expected value of y minus mu y the whole squared. So using this, we define the covariance between x and y is we actually take one function from here. So we write it to be expected value of x minus mu x multiplied by y minus mu y. So this is the definition for covariance. So if you expand this one, here you get expected value, you get four terms, xy minus x mu x, x mu y minus mu x y plus mu x mu y. So if you expand that, you get first term is expected value of xy. Second term is minus expected value of x multiplied by mu y. Third term is minus mu x multiplied by expected value of y. And the last term is plus mu x mu y, because expected value of a constant is itself. But notice that this is mu x, this is mu y. So you have mu x mu y minus mu x mu y minus, so this term cancels with this. So you also get the answer to be so you get the covariance of xy to be expected value of xy minus mu x mu y. So I'm going to summarize that here. So covariance of x comma y is by definition expected value of x minus mu x multiplied by y minus mu y. Why we call this covariance is because if you put y equal to x, this term becomes same as this, you get square, that's the variance of x. But we expanded and showed that this is the same as expected value of xy minus mu x mu y. So because of this minus, this could be positive or negative, and expected value of xy is of course xy fxy x comma y dx dy, double integral. So one need to compute this quantity and then subtract the product of the means of x and y to compute the covariance. Now there is a special case, look at here. Suppose x and y are independent random variables. Then the first term is the same as the second term. So if x and y are independent, we see that the covariance is, this term is the same as this. So the covariance is 0. So covariance of xy, which is expected value of xy minus mu x mu y. But expected value of xy is the product mu x mu y, so this will be 0. So if x and y are independent, the covariance is 0. Now, a normalized quantity of the covariance is defined as the correlation coefficient. So notice that you have variance here sigma x squared, you have variance here sigma y squared, and you have the covariance here, which if you want you can write it as expected value of xy minus mu x mu y. Now we define the correlation coefficient is the same as the covariance except that it is normalized. So this is going to be the covariance of x comma y divided by sigma x sigma y. So this will be expected value of xy minus mu x mu y divided by sigma x sigma y. Now you may say, why is sigma x sigma y? I'm going to show that if you divide by this quantity, the covariance is always less than or equal to 1. And that's the reason we call it the correlation is going to be less than or equal to 1. So I'm going to show this. But before I do that, again, let's see here. If x and y are independent, we saw that the covariance will be 0 here. Covariance will be 0. Consequently, if the covariance is 0, the correlation coefficient also is 0. So when two random variables are independent, then their correlation coefficient is 0. Or we say it, rho xy is 0. Or this is the same as saying that x and y are uncorrelated, no correlation. Uncorrelated random variables. So if x and y are independent, then they are uncorrelated random variables. So we can say that independence implies uncorrelatedness. But not the other way, because we haven't proved it. There is a special case. The special case is, I'll just state the result. When x and y are jointly Gaussian, if they are uncorrelated, they are also independent. But finally, let me just show that why this. So this quantity could have any value. If you divide by sigma x and sigma y, we would have rho to be less than or equal to 1. So let me just to show that before I conclude this part of the talk. So let me consider this random variable z to be ax plus y. So the mean of z is a mu x expected value of z, which is expected value of ax plus y, which is a times expected value of x plus expected value of y by distribution. So the variance of z is expected value of z minus mu z, the whole squared. But z is given to be ax plus y minus a mu x plus b mu y, the whole squared. Whole squared. So we can rewrite this as expected value of a multiplied by x minus mu x plus y minus mu y, the whole squared. So let's expand this. So you get three terms. The first term is a squared multiplied by expected value of x minus mu x, the whole squared, plus 2a expected value of x minus mu x multiplied by y minus mu y, plus the last term is the square of this. That's expected value of y minus mu y, the whole squared. Notice that the first term is this term is the variance of x. This is the covariance between x and y. This is the variance of y squared. So we get here also notice that this quantity has to be positive because the variance is non-negative. So this quantity is non-negative. So I'm just going to copy this. So we have a squared sigma x squared plus 2a covariance of x comma y plus sigma y squared is positive. See, this is a quadratic in A, and it has to be like this because the quadratic is always positive. That means, so if I plot this whole quantity to be FA, I'm plotting FA here. But a quadratic has to have two roots. I don't see any roots here. That means the roots are imaginary. That means its discriminant is negative. So the discriminant is going to be b squared minus 4ac. This is your b, this is a, this is your c. So b squared minus 4ac for a quadratic is here. B is 2 covariance. So that is 4 covariance of x comma y squared. Or you can replace at this point covariance by, anyway, this is good. B squared minus 4ac, 4 multiplied by, a is this, and c is sigma y squared. So this need to be negative. So we have covariance of x comma y, the whole squared, need to be less than or equal to sigma x squared, sigma y squared. Or if you divide by sigma x, sigma y squared here, here you have sigma x squared, sigma y squared, this is 1. So we have covariance over sigma x, sigma y, but that's nothing but the correlation coefficient squared. So we have the absolute value of the correlation coefficient must be less than or equal to 1 because correlation coefficient squared is less than or equal to 1. The correlation coefficient absolute value is less than or equal to 1. So the correlation coefficient can only go between minus 1 and plus 1, including both. But when rho equal to 0, that's a special case. When rho equal to 0, we call it to be x and y to be uncorrelated. Uncorrelated random variables. So the other extreme is when rho is 1, rho is plus minus 1. When rho xy is plus or minus 1, we say x and y are completely dependent or coherent. For example, y is of the form alpha x, then you can see that you can just check it out. Rho xy is 1 actually. So this is like a multipath signal. Y is a delayed version of x. So the signal and its multipath are completely coherent because whatever happens in the signal is the multipath will reflect that after a while. So that's the concept of correlation coefficient and covariance. So the main result is if x and y are independent, then their correlation coefficient is 0. But if the correlation is 0, that doesn't, most of the time, that doesn't mean x and y are independent.